Strasbourg, and he will tell us about Morse de Rham model for surface Yang-Mills measure.
Thank you. So first, I would like to thank the organizers for inviting me and allowing me to give a talk. It's a real honor. So I will report on joint work with Bonthonneau-Chhaibi, Atiyah, Morse-Chhaibi-Rivière-To, Yannick Bonthonneau, and Gabriel Rivière about a certain construction of Yang-Mills measure, but in the sense of differential forms. So the first part of my talk will be devoted to motivating this result and introducing and motivating our main result. So let me start by giving you a kind of motivation about why we are interested in building this Morse de Rham model for Yang-Mills measure by just discussing something which is much simpler than Yang-Mills measure, which is homology. So let's consider a surface, and we would like to, I just want to give you a kind of toy model of impressionistic picture about homology. So given a surface, you can triangulate your surface. Okay, so you have your triangulation. You can consider a certain chain complex made by the faces of the triangulation, the edges of the triangulation and the vertices. Once you're given these chains, you have a certain boundary operator that is denoted by this curly D. And from this boundary operator, given a certain triangulation of your surface, you can define homology groups and calculate their dimension. So the dimension are the Betti numbers. And from these Betti numbers, you can calculate the simplest invariant of a surface, which is the Euler characteristic. So for instance, for the surface is 2 minus B1. And something remarkable about homology and Betti numbers is the invariance by subdivision. So if you are given a triangulation and you refine the triangulation, you get the same numbers. Or if you are given a triangulation and you kill, for instance, here you have this, you kill this edge, the numbers you compute are the same. So this is a fundamental and well-known fact. Euler characteristic does not depend on your choice of triangulation. And it is something, it's helpful to be reminded of this invariance. A second way to compute the homology of a surface is to use Morse theory. And so you consider like a Morse function on your surface. So here I draw the critical points of the Morse function in red. Now the chains of your complex will be made of critical points of various indices. The indices of the critical points will play the role of the dimension of the objects in your chain complex. You have a certain boundary operator. So instead of calculating boundary of a triangle, here the boundary of a critical point will count, in fact, how it will be defined in terms of the critical points connected to A by certain gradient lines. And from this chain complex that you can cook up using the critical points, you also derive the Betti numbers. There is this invariance. If somebody gives you another Morse function, you can calculate the same numbers and deduce the Euler characteristic. In the same way, so you deduce the Euler characteristic by taking number of local maximas plus local minimas minus number of saddle points. And this gives you the same number as in the case of triangulations. And there is also a third way to compute the same invariance of the surface, which is to use differential forms. So I'm an analyst. I like calculus. And so now the objects, your chains, instead of being critical points or triangles, edges, vertices, are going to be certain differential forms. So we work in infinite dimension, which is a huge difference compared to the two other cases. The object that plays the role of the boundary operator will be the de Rham differential acting on differential forms. You need to choose a metric on your surface, define the Hodge Laplacian, and from the Hodge Laplacian, by calculating the dimension of the kernel of the Hodge Laplacian on differential forms of degree I, you also get the Betti numbers. And from this data, you also can deduce the Euler characteristic. But the remarkable fact is that the invariants that you compute do not depend on the choice of metric. Okay, so this is okay. Probably you all know this, but it's just an example that illustrates that there are three ways of getting a certain invariant. And of course, the most painful way is the one by analysis. And the simplest way is drawing triangles. And in this talk, I will discuss about the painful way of getting the Yang-Mills measure. So the one with the differential forms, the elliptic operators, and so on. Okay. So the main character of my talk will be connections. So this is a talk about gauge theory. So the heroes of gauge theory in this talk are going to be Maxwell, so probably the founder of the subject, and physicists Chen-Ning Yang and Robert Mills, who wrote the first paper about the subject in 1954. And in mathematics, Yang-Mills theory became famous. One of the reasons why it became famous was through the work of Atiyah and Bott. So they used Yang-Mills theory to compute, to study the cohomology of moduli space of stable vector bundles over curves. And so this was their motivation to use this equation coming from physics to study invariance of interesting algebra geometric objects. So what's in the Yang-Mills equation? So you start from a vector bundle over a surface. So I give you a surface. The vector space is Cn. And so in my talk, the trivial vector bundles, so surface times Cn. And the object that lives on the vector bundle is called the connection, or sometimes in physics literature, it's called the gauge potential. So it's a Lie algebra valued one form that lives on your surface. And given a connection is a way to prescribe a parallel transport. Okay, so if I give you a connection, and if I draw a curve on the surface by pulling back the connection on the curve, and by solving this ODE, so you see you have a certain ODE, you take your connection, you contract with the velocity of your curve gamma, and if you solve this ODE with initial condition V0, the solution of this ODE describes parallel transport along the curve gamma, and the rule of parallel transport is given by the connection. And so connection, you have to think rule of parallel transport. And if your curve is closed, when you come back to the initial point, the solution of your ODE does not necessarily coincide with the initial condition. And the linear map that maps V0 to V1 is what is called the holonomy of the connection. Okay. And so if you are not familiar with connection, just think about electromagnetism. In this case, the gauge group is U1, so the circle. So that's why it's called abelian gauge, from what I understand, because it's the group is U1. And the holonomy is very easy to calculate. You take your differential form A, you integrate it along the curve gamma, and you compute e to the power I integral of A over gamma. It gives you a complex number of modulus 1, which is the holonomy of your connection. Okay. So now, I'm sorry, I need to introduce some definitions before I state theorems. what can we do with this structure? When you have a vector bundle and you are given a connection, there is a group acting on the whole situation, because if I am given a smooth function valued into the Lie group SUN, this smooth function allows me to change coordinates linearly in each fiber, like you rearrange the fiber. And this infinite dimensional group is called the gauge group. And how does it affect parallel transport? So I told you a connection is a rule that tells you how you parallel transport a certain vector along a curve. So it modifies the vector at the beginning and at the end. And the gauge group acts on the connection nabla by this formula. So there is a certain group acting on the space of connections. This group reparametrizing the fibers. And an important quantity that you can calculate given a certain connection, which is a kind of generalization of the magnetic field, is the so-called curvature of the connection. So first, the formula for the curvature, I give it here. And if you're not familiar with this kind of formula, let me explain to you intuitively what it means. So the curvature is a two-form on your surface valued into the Lie algebra. And the meaning of the curvature is infinitesimal holonomy when your path is a very small square. At least I take it from Arnold, and probably he knows what he's talking about. So I took this picture from the book of Arnold, who explained that this curvature is the measure of infinitesimal holonomy along small square. And this curvature transforms under the action of the gauge group in a very simple way, in a much simpler way than a connection. The curvature gets conjugated by G. Okay, so that's all you need to know about the main character of gauge theory. So this is the connection and its curvature. And so in Euclidean quantum field theory, one of the goals is to compute certain measures on certain space of fields, exactly like in the previous talk by Professor Lenzner. So you are given a certain fields. So here I give you an example. For instance, you look at the H1 function over your surface. These are my fields. And I'm giving a kind of cost function. So here let's say I'm given the Dirichlet energy over the functions on my surface. And I'd like to study or give a meaning to exponential of minus my cost functions times d phi. So a kind of a Gibbs measure on the space of functions. And if I can make sense of this Gibbs measure, then one could say that I constructed the quantum field theory whose fields are these functions over the surface. So in the case of the Dirichlet action functional, this measure is well known. It's the Gaussian free field or free boson in physics literature. And once you are given this measure, what you want to compute are correlation functions. So here, you just take endpoints on your surface. You consider the products of fields at these endpoints, and you calculate the average. And this average is called the correlation function. And so, okay, so this is like summary picture of free fields. And I want to, in analogy with free fields, I want to describe what we would like to do in the case of Yang-Mills. So what replaces functions are connections, but you are not constructing a measure on the space of connections. You are constructing a measure on the space of connection modulo gauge. That's one of the difficulty. What replaces the Dirichlet action functional is the Yang-Mills functional. So you are taking minus trace of curvature wedge star curvature. So your action functional is minimized when the curvature is 0. And so it's that's your cost functional. And you want to give a meaning to this Gibbs measure, e to the power minus Yang-Mills functional dA, and there are many people who have worked on the construction of such measures. So some works in physics that go back to Migdal in the 70s, with Witten in the 90s, so which is more formal. So they get the formulas for the correlation functions. In probability, there are works by Gross, Driver, Sengupta, and Lévy, who construct a holonomy process. So it's a machine that eats a loop and gives you a random matrix, because if you believe that the measure is constructed, the measure on space of connection, it eats loops and it gives you the holonomy of the random connection along the loop. So it's a random matrix. So this construction was the product of the work of these authors. And most relevant for my talk is a work of Chhaibi-Rivière in 2018, where on the flat torus, so he works on the torus T2 with the flat metric, he was able to construct a measure really on the space of connection, but his connections are singular, so distributional connections. Like in quantum field theory, I mean the GFF. Here in yellow, I copied from Google a sample of the GFF. You see, it's not a nice person. It's a very wide object, very rough object. So here, for the case of Yang-Mills, we are also going to construct measures that lived on, that charge very rough objects. And what plays the role of the correlators in the Yang-Mills theory are the following objects. So for instance, if you are given a closed curve in your surface sigma, you would like to calculate average of trace of the holonomy of your random connection along the closed curve gamma. So these are called average of Wilson loop observables. And the analog also of correlation functions would be as follows. You consider endpoints on your surface, and you consider a space of all connections whose monodromy along the point number 1 is conjugated to the angle θ1, etc. And when you calculate the average of such connections, these give you the analogs of correlation functions in the case of the GFF. Okay, so it's all about, I mean, correlation functions in this Yang-Mills thing is all about holonomies. Okay. So the result I'm going to state is very much inspired by work of Thierry Lévy. Probably most of the stuff I know about Yang-Mills, I learned by listening and asking questions to Thierry Lévy. Was very much inspired by work of Bruce Driver in 89, Chhaibi-Rivière, and also Witten. So Chhaibi-Rivière, as I told you, has constructed this measure on the connections living on the flat torus T2. So let me just give a slightly unprecise version of our main result. So G is a compact Lie group. You are given your surface sigma. So what we do is that we construct a measure on one form over the surface sigma valued into the Lie algebra. This one form gives trivial parallel transport along certain lines that I draw in purple. And these one forms, these random one forms, are singular. So they are not smooth one form, not C1 one form, but they are rough objects. So here I give you the regularity of the objects, so Sobolev -1 minus. And we can make sense of the holonomy of these random one forms along a certain class of curves. And we can recover formulas that were found by Witten in the 90s. So we can calculate the mass, the total mass of this measure. So it can be expressed in terms of irreducible representation of your group G. Yeah, it's just a comment. What is interesting also in working in a Yang-Mills measure is that you are not only interested in constructing the probability measure, but also the full measure and its mass. It's very important not to normalize things. Okay, so the mass of the measure has a special value. And I just want to comment that if you let the area of your surface goes to 0, the partition function or the mass of your Yang-Mills measure is related to volumes of character varieties, so volumes of the space of flat connections. And also, if you're given a closed curve gamma, for instance, here I give you an example of closed curve gamma, which dissects the surface into 2 pieces. You have a formula for the average of a certain class function applied to the holonomy of the random connection A along gamma. And it is given in terms of the area of the 2 subsurfaces, which are separated by the curve gamma, and the Euler characteristic of the subsurfaces. So I just want to make a quick comment. Don't worry about the formulas. I just write the formulas so that I have something on the slide, but it's just that this is almost a topological formula. If you look at the formula, except that you have a dependence on the area. So sometimes people say that 2D Yang-Mills theory is almost a topological theory. It's just that it is an area-dependent topological theory. This is the only thing you have to keep in mind and to take home a message. Okay, so area-dependent topological theory.
So,
Yeah.
so what's the formula for a sphere or for a torus?
Yeah, I'm cheating. No, it's a super question. Let me try to. Let's say that these formulas here are in. There are, for instance, for the sphere, the formula is different from here. It's for genus greater or equal to 2, and it is why I say it is a super question, because for instance, if you let the area goes to 0, you see that for sphere and for torus there are problems in my formulas, because in fact the Euler characteristic, when the Euler characteristic is negative, this is the only chance for this formula to converge when the area goes to 0. So sphere and tori need separate discussions.
The formula, the character and the other characteristic look the same.
I know. It's but yeah, it's a way to, because you are following so well. Of course. Yeah. There is
Was done for a reason, I see.
Yeah. There is a chi is a character, and chi of sigma is the Euler characteristic of the surface. Yeah. In fact, yeah. To answer your question, in the case of the sphere and the torus, the measure is a bit more degenerate than in higher genus. For some mysterious reasons, like you cannot construct a metric of negative curvature on the sphere and the torus. Kind of same reason. Okay, so here I have to connect with the title of the program. So I will say very vague things. So this Yang-Mills measure, why it is it seems to be related to certain topological theories in 3D and certain topological theories in 2D. It seems to me, when I read this Witten paper, that there is a triangle of love between Yang-Mills theory when the area goes to 0. It is called the BF theory in the physics literature. It should be related to Chern-Simons, but for a very special 3-manifold. So when the 3-manifold is a surface cross a circle, which also should be related to a version of Vesumino-Witten called the G Vesumino-Witten. Okay, so maybe don't ask too much questions, because this correspondence for the moment is beyond my pay grade. So I don't understand. It's just I will focus only on the Yang-Mills. But this seems very intriguing, at least to me, to understand this correspondence. Okay, so now in the second part of my talk, I will explain how we construct this measure, and the first step is to gauge fix. So I will explain to you what does it mean to fix a gauge. Recall that we want to, your Yang-Mills action functional is invariant by the gauge group. Since it is invariant by the gauge group, your measure does not live on the space of connection, it lives on the space of connection modulo gauge. So the thing is that what you would like to do, So instead of constructing a measure on the space of connection, you want to construct a measure on the orbit space under the gauge rule. What we are going to do is that we are going to slice, in fact, the space of connection, and we are going to try to construct a slice which is transverse to the orbits of the gauge rule. And everything is contained in the way in which we slice the space of connection. So what we do is that we introduce a new gauge. It's not really a new gauge, it's giving a new name to an old person. So there is an old idea from physics that goes back to the 60s, which is called the axial gauge. So if, imagine your surface was the plane, R2, then you can make a certain gauge transformation on any connection on the plane in such a way that you kill parallel transport along the x1 axis. You see what I mean? Like your connection, if you do parallel transport in this direction, is stripped, okay? So once you do this gauge transformation, which is called an axial gauge, your connection has only x2 component. So if I use coordinates x1, x2, you only have x2 component. And if you calculate the curvature of this connection, you see that the curvature is dA. The term with the A wedge A vanishes. So this is really the key observation, that on the plane, if you impose the axial gauge, your curvature is dA, and your Yang-Mills functional becomes quadratic in A. So, okay, to say it in maybe in physics language, your theory is free on the plane. In fact, it's a free theory on the plane. So that's if you do the correct gauge fixing. Of course, the problem is that on the surface, the topology of the surface obstructs this gauge. You cannot impose, I mean, at first sight, an axial gauge on the surface, because you don't have this, the analog of the parallel to the x1 axis. Yes?
But that doesn't kill all the gauge freedom, no, to meant. You still have some remaining gauge freedom.
Yeah. It's partial, but the message is it makes it Gaussian. Even this partial, even imposing this partial condition makes it free. And that's what I want you to keep in mind, that in fact, locally, the theory can be made free in some sense, okay? And on the surface, because of the B1, you cannot, I mean, at first sight, you cannot do it. So the main idea, our main idea is to use Morse theory, to use a certain dynamical system on the surface to impose, in fact, a kind of geometric analog of this axial gauge, and to see what it gives us. Okay, so we were inspired by work of Morse, Harvey Lawson, Lodenbach. So so let me just give you one slide to summarize everything you need to understand what I'm going to talk about Morse theory. So assume your surface is this torus. You have this Morse function, which is the height function. I represented in purple the flow lines of this Morse function. It has one minimum, one maximum, two saddle points. Near the saddle points, you have special lines that are called the unstable curves that I represent in red. And you have blue lines that are called stable curve that I represented in blue here. So, okay, so I'm given a certain dynamical system on my surface. And this is the cartoon picture of what we are going to do. So instead of working with smooth connections, we have to accept working with singular connections. So we have, in some sense, we have to compactify the space of smooth connections by allowing singular connections. And in some sense, instead of working with the smooth gauge transformations, we have to accept working with gauge transformations which develop certain singularities. Okay, so we are going to consider gauge transformation which develop certain jumps along the unstable curves. So you see here, I gave you a kind of picture. I tried to draw, I tried the best I could to draw you a picture of certain gauge transformation where you see that it jumps along the unstable curves. And this jump, you have to think of this as like San Andrea gap, you see? So your gauge transformation is going to jump along the curve. And let me explain, in fact, where it comes from. So to understand why we should consider this gauge transformation with discontinuities, you have to think this business of connections in terms of a moving frame. So if you are given a connection, and if I give you a certain moving frame on the bundle, then the matrix coefficients of your connections can be calculated in terms of the moving frame, okay? And making a gauge transformation, you can think of it as changing the moving frame. So looking at a certain connection on a new frame is exactly the same thing as doing a gauge transformation. Now you consider your surface. You start from the minimum. You take a certain frame at the minimum. Then you use the dynamics of the Morse flow to parallel transport your frame from the minimum to the whole surface using your connection, nabla there. And then when you consider the connection in this new frame, parallel transported from the minimum, you will see that, in fact, your frame, here I kind of try to make a picture, your frame, in fact, develops discontinuities along the unstable curve. Your frame will jump when you cross an unstable curve, and this jump in the moving frame is responsible for the fact that your new connections in this moving frame will develop certain singularities along the unstable curves. So here is a theorem that we prove. So this has nothing to do with quantum Yang-Mills. It's just classical Yang-Mills, okay? So if I'm given a smooth connection on the surface, and if I solve a certain transport equation, okay, don't worry about transport equation. Just think about my frame, my blue frame in the previous slide, which is defined by parallel transporting along the integral curve. Then what we prove is that when you write your connection in this new frame, in the blue frame, it writes as a certain one form. And this one form, when you contract it with the vector field, you get 0. So the parallel transport along the integral curves of your flow is 0, plus certain sum of Lie algebra elements times some delta currents that are supported on the unstable curve. So it's just, so the take-home message is, if you want to impose the axial gauge, an analog of the axial gauge on a surface, you must accept that your connection will develop defects, and the defects will be along the unstable curves. And the unstable curves, they act as defect lines. And now the connection that you get on the right-hand side is singular, but the parallel transport will be trivial along the flow lines. And it's just a comment, so a relation with a flat connection, the character variety. What happens if I started with a flat connection? If I apply my procedure, my gauge transformation to a flat connection, what I get is a sum of delta supported connection along the unstable curve. So this gauge transformation gives us a Morse theoretic model for the character variety. So any flat connection can be reduced to a sum of Lie algebra element times some kind of currents carried by the unstable curves. And if you look at because you started from a connection, for instance, on the torus, and the holonomy of the connection on the torus along an infinitesimal loop near the maximum should be the identity, then if you write this condition for the singular connection, it gives you a certain presentation of the surface group. So in fact, our gauge transformation allows us to interpolate between the world of smooth connections and the combinatorial description of the character variety. So it gives us a bit like Okay, if you are familiar in analysis with the Witten Laplacian is a way to interpolate between Hodge theory and Morse theory. So here it's a kind of analog in the world of gauge theory of the Witten Laplacian, in some sense. Okay, so now let us see what it gives us at a quantum level. So let us examine the consequence for the measure. Okay, so assume that we have our Morse gauge, so we can slice the space of connection by connection whose parallel transport along the flow lines is trivial. So you take your one form, and when you contract it with the vector field, you get 0. So as I told you, now the Yang-Mills functional for this kind of Morse gauge fixed connection becomes quadratic in A. Okay. And now what you are going to do is that you are going to make a change of variable in your functional integral. So now what I'm going to do is that, how can I say it? The Morse gauge is like a kind of change of coordinates in the path integral. And now I'm going to see what it gives me for the functional integral if I write my theory in this Morse gauge. So what we are going to do is that we are going to introduce a change of variables. So maybe let me use the blackboard to do this change of variables here on the blackboard. So you want to give a meaning to this functional integral. And instead of integrating over all A, you integrate over all A which live on your slice. So all A such that A contracted with the vector field V that generates your dynamics on the surface equals 0. So this is your slice. This is your slice. You consider the functional integral over your slice. So what you are going to do is that you are going to make a change of variable. You are going to write your connection A as a certain, in fact, your change of variable involves setting B equals VA. So B is a 2 form, so it's a 2 form valued into the Lie algebra. And you will write your connection A in terms of B. So formally, A is the D minus 1 of B plus the topological correction, so sum over log of GA. So Lie algebra elements where A runs over the critical points, the saddle points of your Morse function times certain delta distributions carried by unstable curves. And once you do this change of variable, you see that your Yang-Mills measure becomes a Gaussian measure over B times certain product of group elements in the Lie group that are indexed by the critical points of index 1 of your Morse function. And these Lie group elements, they play the role of the 0 modes, in fact, of your theory. So in fact, here, if you want, this decomposition, it is reminiscent of the Hodge decomposition. And here are the 0 modes of your theory, in some sense. And the functional integral is Gaussian over B. Okay. So now I will describe how we give, once we make this formal change of variable inside of the functional integral, I'll just explain quickly how we can give a probabilistic construction, in fact, of these objects. So here, the field B, this measure is called, sometimes called the white noise. If you are familiar with the white noise, so if you are unfamiliar with white noise, I give you a kind of intuitive definition. You assume that your surface, you can triangulate it. for each triangle, you consider the indicator function of the triangle. You divide by the area of the triangle, and you multiply by a independent Gaussian random variable for each face. And then you let the size of the face goes to 0. So this will converge to the white noise. So it's a very rough object. It's a random distribution of regularity -1 minus. And what we are going to do is that we need to somehow we need to invert the de Rham differential. We need to invert it on the white noise. And so what we do is something I can explain in a geometrical way. So here, if you are given your surface, and if I give you a point M, the Gaussian part of my connection will be the integral of the white noise over the flow line that goes from the minimum to M. Okay, so if you integrate this 2 form over this flow line from the minimum to M, you get the Gaussian part of the connection. And so that's one step of our construction. Another important feature of our random connection is a certain spatial Markov property. So for instance, here I compare to the Brownian motion. So if you're considering a Brownian motion on the real line, so BS2, so you have 2 times S1 and S2, and S2 is greater than S1, then the knowledge of BS2 conditional to what happens before S1 is the same thing as BS2 conditional on BS1. And in our case, our random connection also satisfies a certain Markov property, but the role of time is replaced by the levels of the Morse function. So what we do is that we construct our measure inductively on the levels of the Morse function, and we prove a certain surface Markov property is that if you're, for instance, here in the picture, if you are given the 2 loops, gamma 1 and gamma 2, what we prove is that the holonomy of the random connection over gamma 2 conditional to A on the whole surface, which is below gamma 1, is the same as the holonomy of the connection over gamma 2 conditional to the holonomy over gamma 1. So a kind of surface Markov property for our random field. And this surface Markov property is one of the main reasons why we can get the explicit formulas that I showed you that were due to Witten. So maybe for some of you who are in CFT, one can reformulate this surface Markov property in terms of Segal amplitudes, if you want. Like you can construct Segal amplitudes in this Morse de Rham model by considering the functional integral and putting a kind of boundary condition, in fact, on the functional integral. So if you have a surface, a border surface, and you integrate over all connections, and you prescribe the holonomy at the in component and at the out component, you get the analog in the 2D Yang-Mills case of the Segal amplitudes. And I think I want to stop here, and I would like to thank you for your attention.
Viet, other questions? No?
You mentioned one of the difficulty was quotienting by the gauge group.
Yeah.
I guess, is it possible to define a theory when you don't do that? And it looks actually that it will be harder because then it's not quadratic.
Yeah.
So it will be actually harder not to quotient then.
Yeah, I think it's much easier if you gauge, and if you choose the correct gauge where the action functional becomes quadratic in parts of the variables. Because if you keep the interaction, the construction is very difficult for 2D Yang-Mills. It's for for instance, if you take the I don't know, Coulomb gauge, then you still have the nonlinear part. And it's very hard to treat. It's not like in scalar theories where you have certain positivities that help to construct the functional measure, like in P-phi2 or phi-4-3, where you can deal easily with the nonlinearity. Here for gauge theories, since things are vector valued and differential forms, it's at least for me, the best way to go is to find the best gauge that makes things as simple as possible. That's what I would say.
Any questions?
So if I remember well, one of the motivations for Ilya's work was also to get kind of nice regularity for the connection. So it would be locally like the regularity of vector value GFF.
It's super remark. Here is much worse.
It's much
Okay.
worse, right? Because
So
one direction is
exactly.
nice, the other
So
is,
exactly. So his regularity, Chebyref, is 0 minus. It's a GFF regularity. Here, our gauge is so wide that our connection is Hölder roughly Hölder 1/2 minus along the flow, and perpendicular to the flow, I mean orthogonal to the flow, it is minus 1/2 minus. So in fact, our random connection is lives in an anisotropic space. In this direction, it sees a high regularity. I mean, not crazily high, but and here it is very rough in this direction. But this is the price to pay to get.
and you have any hope to try to make it more regular, or to have this isotropic regularity, or this?
Not for this kind of gauge. And also, it's our connection is super wide along the defect lines, because you have delta. It becomes a delta connection along the defect line. So it's.
Okay. Could this kind of ideas be applied for in a higher dimension? Not surfaces, but
I've been asked the question many times, and unfortunately for me, at least for me, for 3D young mills, it fails miserably. It's a very bad idea to choose the axial gauge for 3D young mills, because first, it doesn't kill the nonlinearity. So no, but here you see that the theory is totally miraculous. I mean, it's a kind of an integrable theory. In 3D, I don't kill the nonlinearity, and the gauge makes the connection so singular that I cannot, I mean, for renormalization, it is not easy to renormalize the nonlinearity in this gauge. I think for 3D, you have to use more clever gauge that are more democratic in the irregularity, in the roughness.
If you take two different vector field, can you relate your measure, or it's not absolutely continuous?
Yeah, the measure, they charge completely different things if you take two different dynamics. But still, the average on gauge invariant observables is the same, of course, because we want it to be the same.
But this you have to go through the formula of Migdal and so on. No? It's hard to prove it directly.
Yeah. We go through the formula of, like we calculate the n formula, and we see that the n formula does not depend on our choice of Morse function. But maybe there is a way to transport certain measure to the other one, but I would need to think. But your question could also be asked even for the model of homology, when you have the model of homology using Morse function, and somebody gives you another Morse function, and you would like to compare the chain complexes. You could say that if I calculate the same Betti numbers as with triangulation, and since I know Betti numbers are invariant, then I know I'm calculating invariance, or I can try to calculate directly how things change when I change the function. So probably, yeah, we should think hard in this case how to see how the measure transports.
Maybe comment more on Chernow-Simon's theory, relations to Chernow-Simon's theory you mentioned.
Yeah. Oh, wait a second. Yeah. is my vague understanding, it's not clear at the moment, is that when the area goes to 0, I showed you the formulas. You see there are topological numbers like Euler characteristic, irreducible representation of your group, and area. If the area goes to 0, the theory is topological. It's called the BF theory. So it's just a.
I think in terms of triangulation, when you take limit of triangles to 0 or what? In terms of triangulations.
In terms of triangulation, you can write correlators of the area goes to 0 theory. Yes, in terms of the triangulation, and it gives you. I can say more. I can be more precise. Let's say that you have a certain measure on the space of flat connections, and you know that the space of flat connection is finite dimensional. Okay, so let's say that here. Okay, maybe I have a slide. If I'm lazy, I have a slide prepared for this comment. I'm sorry. Okay, so here curvature equals 0. I represent it red. Okay, I have my measure, which is a charge infinite dimensional space. When the area goes to 0, my measure concentrates on the space of flat connections, which is finite dimensional. And so if the area goes to 0 limit, the theory, the functional integral is over a finite dimensional space, like the moduli space of flat connection with its natural symplectic measure, okay, symplectic volume. And it makes the correlators topological. And the relation with the Chern-Simons goes as follows, from what I understand. It's in Witten paper, but I can try to explain very quickly, is that when the area goes to 0, you are calculating volumes of character varieties, if you want. And another way to recover these volumes of character varieties is by the Verlinde formula. Because in the case of the Verlinde formula, if you look at certain asymptotics, like Weil laws, you get factors that give you volumes of space of flat connections modulo gauge. And the relation with Chern-Simons goes through this observation. Volumes of character varieties and Verlinde.
But in Witten, if I remember, he computed the Chern-Simon action for this product.
Yeah, sigma cross S1.
And he showed Young-Mills basically.
No, yeah, up to something. He shows it is related to area 0 limit of Young-Mills. He shows it is related to BF.
I remember some sort of Fourier transform.
Yeah. So if you, I can make a comment. You start from. That's the path integral for Young-Mills. You make a change of variable, like infinite dimensional Fourier transform, by introducing an auxiliary field. And now if you let the area goes to 0, it kills this term. This term becomes 1. So what you get is EFB integral over dB, dA, and you recognize formally, imagine A and B are real variables. You recognize delta of f of A, okay? So this is in fact, it's done. I'm sorry, but it is what's written in Witten's paper. Imagine this, you are in finite dimension. You are, and here is the measure on the flat connection, because this is a delta function applied to the curvature. Okay, so it's the area 0 limit of Young-Mills, which is supposed to be related to this Chern-Simons theory on the surface cross S1. That's how the correspondence goes.
It can't possibly be finite area because there's no area in Chern-Simons anyways.
Yeah. Voila. Another remark is that Chern-Simons is topological, and I told you this is area-dependent topological theory. So if you let area is 0, then it's topological. So it's really through the 0 area theory.
But where is the level then?
Excuse me?
Where is the level in the Chern-Simons?
I think the level is related to, because in Verlinde, you try to calculate certain asymptotics. So you see in the space of flat connection, so from what I remember, they consider a certain natural line bundle over the space of flat connection, and you calculate dimension of holomorphic section of tensor powers of this line bundle of the space of flat connection. And I think this K is related to the level.
Okay, no more questions. Thank you yet again.